So, good evening, everyone. I hope you're all doing well. So, let's continue our discussion of chapter 4 of the textbook. So, we will now discuss the beta distribution. Before doing that, we will first introduce the notion of the beta function, which is another special function commonly used in probability and statistics and other domain also. So the beta function is defined via two parameters, alpha and beta, both of which are positive. Then the beta function with these parameters alpha and beta, unfortunate naming because the function name is also the name of the parameter. But in any case, that beta function is defined via this definite integral here. So this integral looks reasonably simple, each for say like alpha and beta small. So for example, let's say alpha equal to 2, beta equal to 1, then this is nothing more than the integral from 0 to 1 of t dt. And so that should give you 1/2. But then what happens if say alpha equal to say like 0.5? Or say alpha equal to say pi? So what is the value of this function? And it turns out that there is a key link between the beta function and the gamma function as given by this equation here. So this equation here is a bit, I would say, magical. Because if you remember, gamma of alpha is defined via the integral from 0 to infinity of t alpha minus 1 e minus t dt. So this integral here depends on the exponential function. The integrand goes from 0 to infinity, while here the integral goes from 0 to 1. So the integral is bounded. Here the integral is unbounded. And furthermore, there are no appearance of the exponential function anywhere. Where is Waldo? Or where is E? Between the relationship. So it turns out that this relationship here can be proved using, I think, another quite ingenious change of variable, Jacobian transformation. So this is problem 4.197 in your textbook, done in a slightly different flavor. But in any case, as we recall, if we write gamma alpha and gamma beta as two integral, the first integral use x and the second integral use y, then we can combine this into a single integral as follows. And now we will do a change of variable transformation. We will let x be st and y be s1 minus t so that the sum is equal to s. This implies because x is bigger than 0 and y bigger than 0, this implies that t has to be in the interval 0, 1. In any case, we can now define the Jacobian matrix for this change of variable to be this matrix here. So this is dx over ds, that is just simply t, dx over dt, that is simply s. And similarly for the remaining term. So now by the change of variable in your multivariable calculus class, the area volume dx over dy is the same as ds over ds by dt, with ds times dt, multiplied with the determinant or the absolute value of the determinant of J. The determinant of this one is a 2 by 2 matrix, is easy. The determinant of this one is nothing more than t times minus s minus s 1 minus t. That should be the same as minus s. And since you're taking the absolute value, it's just absolute value of minus s, which is s ds dt. So now with this change of variable as mentioned, the integral which we have expanded out to be this form, and then now this is our x, this is our y. So you will have s to the alpha minus 1, s to the beta minus 1, and then another s, so that's alpha plus beta minus 1, or alpha minus 1 plus beta minus 1 plus 1. And similarly for t to alpha minus 1, and 1 minus t to the beta minus 1. And so this integral here depends on s only, so you can move it outside the first integral. And this is nothing but than gamma of alpha plus beta. And this is the definition of b of alpha beta. And so you get the statement or the result as we claim. So equipped with this definition for the beta function, we can then now define the beta distribution. So we will see the beta distribution maybe later in chapter 6 again. So we'll revisit this later. But in any case, a continuous random variable x is said to have a beta distribution with parameters alpha beta plus 1. This is a shape parameter 1. And this is another shape parameter 2. If x has a PDF of this form. And this PDF is well defined for x inside the interval 0, 1. So this b alpha beta here is nothing more than the normalizing factor, because as we recall, integral of x alpha minus 1, 1 minus x beta minus 1, dx is b of alpha beta. So this is just the normalizing factor. Normalizing so that the PDF integrates to 1. So we write this as x beta alpha beta. So as an example, when alpha equal to beta equal to 1, then b alpha beta is equal to gamma of 2 divided by gamma of 1, and there's nothing more than 1 factorial divided by 0 factorial is equal to 1. In which case, furthermore, x alpha minus 1 minus x beta minus 1 is simply also 1. So the beta alpha beta reduces to a uniform distribution. So the beta is a generalization of the uniform. To continue this example further, suppose we have u which is uniform, and we defined x which is u to the power of alpha for alpha bigger than 0. Then by the result on the monotone transformation, we have this as the PDF for x by the monotone transformation. So see your lecture note earlier. So this we say agrees with the PDF of a beta 1 over alpha and 1 random variable, because in this case b of 1 over alpha 1 is gamma of 1 over alpha plus 1 divided by gamma of 1 over alpha and then gamma 1, which is the same as gamma of 1 over alpha times 1 over alpha divided by gamma of 1 over alpha gamma 1. And so this cancel out. This is just 1, and so you get 1 over alpha here. So it's a PDF of a beta 1 over alpha 1. So the beta distribution is quite closely related to the uniform. So as another example, so the beta alpha beta is only supported on the interval 0, 1. That's what we say here. So if we shift and scale a beta random variable by shifting and scaling it like this, then we get something that looks like a beta. But now that random variable is not defined on the interval CD. So CD could be arbitrary, just finite, with D bigger than C. And then this is a location scale transformation. Location scale transformation. So earlier in your lecture note, we know the PDF for the location scale, and that simplifies out to be this expression here, which looks very much like the beta, like the PDF of a beta random variable, where you make the rule that x is just z minus c divided by d minus c in interval 0, 1. So that's where you get this term here with a change of variable. So finally, if x is beta alpha beta, then by getting y, which is 1 minus x, you swap the parameters. So alpha becomes beta and beta becomes alpha. So try to go to this link, so you can click on the link and play around with the value of alpha and beta parameters. You can input your own numbers to see the diverse shapes of the beta random variables. So for example, let's consider here, these are the shape of the PDF for several choice for beta, alpha beta random variable. So this blue line here, the blue is alpha equal to 2, beta equal to 1. The brown is alpha equal to 1, beta equal to 2. So that's the usage translation. This here, this orange is alpha equal to beta equal to 10. This green here is, if I remember correctly, alpha equal to 10, beta equal to 2. And this here is alpha equal to 2, beta equal to 10 for this cyan. And this red here is alpha equal to beta equal to 0.2. So we see the very shape. So the red here looks like this. The red here is a U shape. The orange is bell shape. That looks kind of like normal. This is kind of like a gamma shape. Gamma shape for small, let's say alpha. And this is another kind looking like alpha shape transform. And this looks like a triangle shape. So as you can see, the beta random variable has many different shapes. Okay, so the beta distribution turns out to be very popular used in what is known as Bayesian statistics. So you may take a look at this one in maybe you get a glimpse in 422. But in any case, the beta distribution is known as a probability distribution over probability distributions. So let's see what this means. Because a beta random variable takes value in 0, 1, and that many discrete distributions, such as the binomial, geometric, negative binomial, hypergeometric, are constructed using a sequence of Bernoulli trials, if we now assume that the probability of success are unknown, in general, we never know the probability of success anyway, we have to estimate it. So we assume it's unknown, and we will model it by a random variable taking values in 0, 1. Then, because the beta random variable takes values in 0, 1, we can model P as a beta random variable. And due to the many shapes for the choice of alpha and beta, the diverse parameters, this allowed us to generate a diverse suite of distribution. See here, many different shapes for the beta. So one the classic example is this example here on what is called as the beta binomial random variable. So here X is a binomial with n trials and probability success P. But now P is modeled as a random variable. So instead of thinking of P as being fixed, we think of P as being random. So then what is the probability mass function for X look like? Well, let's think. So this is the probability mass function for X if we assume that P is fixed. But because P is not fixed, P is random, we have to introduce this here as the PDF for the randomness, for the beta alpha. Because P we assume is random, so then P is a random variable, so we have to introduce this PDF. And therefore we have this normalizing factor here. But if we move nk out, then this integral here is nothing more than the function integral from 0 to 1 is nothing more than this beta k plus alpha for k plus alpha minus 1 and n minus k plus beta for n minus k plus beta minus 1. This is nothing more than the beta function with those parameters. And we recorded beta of alpha beta is gamma of alpha, gamma of beta, divided by gamma of alpha plus beta. So after some simplification, we get this by using those definitions. And then once again, we recorded gamma of alpha is alpha minus 1 factorial if alpha is integer. So we can replace nk with gamma n plus 1 for n factorial, gamma k plus 1 for k factorial, and gamma m minus k plus 1 for m minus k factorial. So we get this maybe messy looking expression, but still simple in terms of the gamma function only. So in the case when alpha equal to beta equal to 1, then the above expression simplifies to this PMF, which is nothing more than the PMF of a discrete uniform random variable. And so if alpha equal to beta equal to 1, we get discrete uniform. If we let alpha and beta be big numbers and the ratio converges to some p star, such as for example e.g. alpha equal to 10,000 and maybe like beta equal to 20,000, in which case p star is roughly 1 over 3, then x looks like binomial n of p star. So by choosing different shape, we get different distribution. So this justified the meaning of a distribution over distributions. By choosing the alpha and beta parameters, we can induce other distributions. Okay, so let us now compute the mean and the variance of beta random variable. So as an aside, I just want to note that there are no simple expression for the MGF for the moment generating function of a beta random variable. But the mean and variance has simple expression. So the expected value of x, the mean is alpha over alpha plus beta, and the variance of x is given here, a bit more complicated. But the proof is quite straightforward, just direct calculations by the diffusion of the beta function. So this is the expected value of x. So here's b alpha beta, and then you have x alpha minus 1, 1 minus x beta minus 1 for the PDF, and then you also have x times fx to get the expectation, so that becomes this term here. And this integral here is nothing more than this beta alpha plus 1 beta function. And then this is the relationship between the beta and the gamma, beta and gamma function. And then this is simplification because gamma of alpha plus 1 is alpha gamma alpha. And similarly, gamma of alpha plus beta plus 1 is alpha plus beta gamma alpha plus beta. So you cancel this one out, gamma alpha plus beta versus gamma alpha plus beta plus 1, and gamma alpha plus 1 versus gamma alpha. The expression for the variance is similar, so now you just have x alpha plus 1 here for the integrand, and that becomes this integral here is nothing more than this term here, and then simplification again, where now we use gamma alpha plus 2 is alpha plus 1 alpha gamma alpha. So further algebraic manipulations yield the expression for variance given above. So these are cute, but the most important thing here is, I suppose, is that you can easily compute higher order moments as well as inverse and fractional moments of a beta random variable. So compare this against the gamma. So in particular, if we have x is beta alpha beta, then the expected value of x to the power of c is given simply here. So recall, in the case when x is gamma alpha beta, that the expected value of x to the power of c is gamma alpha plus c, beta to the power of c, divided by gamma to the power of alpha. So try to compare these two expressions here. But in any case, this is problem 4.200 in your textbook, and this allowed us to compute expected value of 1 over x, expected value of say like 1 over square root of x, and so on and so forth. Okay, so our last topic for chapter 4 will be the following relationship between the CDF, the cumulative distribution function for beta random variable, versus the cumulative distribution function for the binomial. So in general, there are no simple expressions for the CDF of alpha beta. However, when alpha and beta are both positive integers, we can relate the CDF of beta to the CDF of binomial. So in particular, if we have this proposition, which is problem 4.134 in your book, let alpha and beta be integers. For x beta alpha beta, then this is the CDF of x, and this is the CDF of, or 1 minus the CDF of a binomial alpha plus beta minus 1 with property x, where x is the property of success here and here. Okay, that the 1 minus CDF of this one is bigger than or equal to alpha, or less than or equal to alpha. So the main point is that we can compute the tail property of a binomial random variable by numerically evaluating the incomplete beta integral. So this is what is done by software. Software does this all the time, because otherwise evaluating the factorials are quite messy. So the proof of this result is just integration by parts. It is straightforward but quite tedious. So a sketch is as follows. We consider this integral here, and we let's say like dv be say t alpha minus 1, and u be say like 1 minus t beta minus 1, in which case v is 1 over alpha t alpha, and then du is beta minus 1 t beta minus 2 with a minus sign in front. So therefore you have this integral here is uv, and then this part is minus v du, and some simple evaluation gives you this as the integration. So now we could do this same trick. So now this here is our probability of capital X less than little x. We defined earlier to be this integral. So here we see its appearance here. And then b of alpha beta will relate to this gamma function. B alpha beta is equal to this gamma function here, or rather 1 over b alpha beta is equal to this gamma function here. And then by our integration by part, we have this first term plus this second term. And then now using the property of the gamma function, we have 1 over gamma alpha, gamma beta, times beta minus 1 over alpha is nothing more than 1 over gamma alpha plus 1, gamma beta minus 1. So that is what we have here after taking case into this one. So now if we define this term here as fx alpha beta, then we see that this term here can now be x alpha plus 1, beta minus 1 by pattern matching. So you have alpha plus 1 factorial, beta minus 1 factorial. Compare here where you have alpha factor alpha, gamma alpha, and gamma beta. Here you have gamma alpha plus 1 and gamma beta minus 1. The sum is still alpha plus beta, as you have here. And in the integration here, you have t to alpha versus t alpha minus 1, 1 minus t to beta minus 2 versus 1 minus t to beta minus 1. And so you have that f of x alpha beta is now this term plus f of x alpha plus 1 beta minus 1. So we have this recurrence relationship fx alpha beta, fx alpha plus 1 beta minus 1 plus this term. So now if you look at fx alpha plus 1 beta minus 1 and you then write it as alpha plus 2 beta minus 2, then you have analogously this term is the analog of this term. So you repeat this a bunch of times, you have this summation here. And now so the base case, so you want to do at the base case is fx alpha plus beta minus 1 and then 1 is equal to what? So this is maybe coffee break. Compute this. But in any case, you wouldn't have, when beta are positive integers, the both sum simplifies to this. We see beta minus 1 appearance here. And then this is the definition of the gamma function. Gamma alpha plus beta minus 1, or gamma alpha plus beta is alpha plus beta minus 1 factorial. And similarly for the denominator. And so now you can do a change of variable by letting I prime be alpha plus I. So I goes from 0 to beta minus 1. Then I prime goes from alpha to alpha plus beta minus 1. So therefore you have I from alpha to alpha plus beta minus 1. Now you have xi, and this is now, this term becomes this term. And this is nothing more than the tail of the binomial, which we say is what appears here, as desired. So as a quick example, let's look at example 4.11 in your textbook. So it says that a gasoline distributor has storage tanks that hold fixed supplies and are filled every Monday. And because this is the proportion gasoline sold each week, because this is a proportion, we want to represent it by some random variable taking value in 0, 1. So the distributor decided to model this random variable as a beta for 2. So what's the probability that the wholesaler will sell at least 90% of the stock? So we will say x beta for 2. We want to know what the probability that x is bigger than 0.9. And so this is just a simple calculation using beta random variable. This integral is easy because integration of x to the power 3 is 1/4 x over 4. And x to the power 4 is 1/5 x over 5. And b for 2 is gamma 6 divided by gamma 4. Gamma 2 is 20. So you have 20 here. And so the answer is 0.08. Similarly, you can evaluate probably x less than or equal to 9, 0.9, in which case you want to sum over I equal to alpha, so I equal to alpha equal to 4, up to alpha plus beta minus 1, which is the same as 5. And then now you will have, then of 5 choose I, and then x, which is now 0.9, x is equal to 0.9 to the power of I, and then 1 minus x to the power of 5 minus I. And so that gives you this expression here, which is 0.92, and that is roughly 1 minus 0.08. So this example here illustrates that you can easily think of the problem either via computing this integral or via looking at the binomial random variable. So with that said, I will end here for today. So please remember that your next homework assignment is due next Tuesday. And please send me an email if you have any questions about the homeworks, about the lectures. And starting from maybe in a few days, we will upload the lectures for chapter 5. So take care, stay healthy, and I will talk to you next time. Bye.